Cache coherence is one property that needs to be guaranteed for parallel programs to work correctly. Another such property is memory consistency, and we'll illustrate that by studying Peterson's algorithm. The challenge is to implement a lock so that only one process at a time can pass the lock and enter the critical section, which is the portion of code that must be executed only by one processor at a time. The code here consists of a while loop that keeps checking a shared variable. As soon as that shared variable becomes 0, the process can enter the critical section. It immediately sets the shared variable back to 1. Then, when the process exits the critical section, it sets the shared variable to 0, allowing the next process to enter the loop. Does this guarantee mutual exclusion? No. Suppose a process sets the shared variable to 0, and then both processes check the shared variable before either process gets to the statement that sets it to 1. In this case, both processes will enter the critical section. So let's take a look at another algorithm that can guarantee exclusion. Peterson's algorithm, first published in 1981, is a software-based algorithm that successfully implements mutual exclusion. It uses two shared variables, a variable turn that keeps track of which processor's turn it is to enter the critical section, and an array called interested that records which of the processes is currently trying to enter. In order to acquire the lock, the process sets its interested variable to true and then sets turn so that it is the other processor's turn. That is, the other processor's turn to enter the critical section. Then, this process loops as long as it is the other process's turn and the other process wants to enter the critical section. The process can finally enter the critical section when either it becomes its turn or the other process is no longer interested in entering the critical section. In order to leave the critical section, the process just sets its interested variable to false. Note that a process can only acquire the lock if the other process is not competing for the lock, that is, its interested variable is false, or it has just left the critical section, or if it's the process's turn that wants to enter the critical section. In this case, the other process will be blocked by the setting of the turn variable. Let's consider how Peterson's algorithm works in a couple of different scenarios. In the first scenario, there is no race. Only one process at a time is trying to enter the critical section. Process 0 sets interested to true and sets turn to process 1. But since process 1 is not interested in entering the critical section, process 0 is allowed to go in. Then process 1 sets its interested variable to true and sets turn to process 0. But since process 0 is still in the critical section, its interested variable is still true, so process 1 can't enter the critical section. Then process 0 exits the critical section and sets its interested variable to true, allowing process 1 to enter the critical section. In this scenario, there is a race. Both processes set their interested to true. Process 0 sets turn before process 1, so after process 1 sets it, turn equals 0. Process 0 now gets to enter the critical section, since turn is pointing to it. Process 1, however, has to wait in a loop until process 0 releases the lock. Then when process 0 does release the lock, it sets its interested variable to false, and then process 1 can acquire the lock and enter the critical section. In our discussion of Peterson's algorithm, we have been assuming that changes to variables are seen by both processors in the same order that they appear in the program. Well, there are a lot of reasons why the operations might be seen out of order. First, the compiler could change the order of the statements so that turn gets changed first. That's because there's no data dependence between the two statements, and the compiler might want to move operations around to get greater instruction level parallelism. Second, even if the instructions are compiled in program order, The architecture could reorder the operations. When a program writes values to memory, it doesn't wait until they're in memory before beginning the next instruction. Instead, it writes the values to a write buffer first, and then the write buffer is flushed to main memory when that memory module becomes free. If some other instruction, say from a different processor, is writing to the same memory module at the same time, the first write may be delayed, and then the following write could complete first. Or the same could happen if turn is located in a nearby memory and interested is in a far away memory. Then the first write could be delayed due to network latency. Finally, if turn is cached and interested is not, the write to turn might complete out of order before the write to interested. This is called a memory consistency problem, and it prevents Peterson's algorithm from working correctly. Let's see what happens when Peterson's algorithm executes on a system where writes can complete out of order. Process 0 sets interested to true. Then process 1 sets its interested to true and turn to 0. Just after that, process 0 sets turn to 1. When process 0 gets to the while loop, turn is 1, so it has to wait. Meanwhile, process 1 gets out of its while loop since turn is not equal to 0 and enters the critical section. But suppose process 0 sees the two writes from process 1 out of order. Then it can enter the critical section before it sees interested 1 equal true. And so can process 1 because it's its turn. This allows both processes to be in the critical section at the same time.